start recording. Let me put focus on Yanis. Yanis sharing is available, so the floor is yours.
Let me share the screen. Hello everyone. Today I'm going to present 3 exercises. First, weak localization, where it's more mathematical, less about physics, but it's quite interesting in the sense that the same methods are usually often used for other fields in physics with the Green's functions and etc. The second exercise is about resonant conjugate manipulation. It's a physical one, and I would say it's not so hard. And the last exercise about constructing the gate C not for 2-qubit system. So let's start with the big localization exercise. In this exercise, we already have been given a formula for conductance correction due to some weak localization effect. And this conductance correction is given. I need to change color. This conductance correction is given with this formula. You see there is a probable integration over time from 0 to infinity, and integration over x of some probability, and this probability is a probability that an electron sitting in a point at point x travels to x prime in time interval t. So if we assume reasonable physics, then you see if let's say if we put t0, then a probability for one particle to go to another place x prime would be 0 if, for example, as we say that the time interval is 0, and this is going to be one of the boundary condition. So and this probability obeys a diffusion equation. So one can imagine that we have an electron sitting in one single place in initial, and over time it's just spreads out into larger regions. So the probability that we have an electron in one place is becoming smaller, and so also this probability for particle travel to one x to another decays. And yeah, on the right of the equation is initial conditions that we have particles sitting in one place and at time 0. Right, so yeah, next slide. So let's start the first question. And the first question gives a task us to integrate the diffusion equation in time and to give a relation for W, which happens to be integral of for P over time. And that's quite easy to do. We start with this diffusion equation, and we apply integrals here and here. When we apply the integrals, we need to see this is a delta function. If we integrate over the delta function, we get in the right side only delta x minus x prime. On the left side, what we see, we have time derivative of p. So left side is p of x prime at first at infinity minus p x prime at 0 and minus now comes interesting part. We just put the integral of t behind, we swaps, puts derivative of x outside the integral, sorry, integral put inside the derivative. And we see we have x prime t and dt. And we, by definition, it's wx prime. So we can put the conditions. We know that at time infinity the particle will be so dissipated that the probability of it traveling from one place to another would be 0. And initially we know that the particle sitting at the same place as x prime, and so it is delta function x minus x prime shown here. And when we plug in, so we have delta function here and we have delta function on the right. We get that on the right we get 2 delta functions, but then we can divide the equation by 2 and we got this factor on this equation. And for on this one we're going to solve. So to solve it, the first step is, so it's an inhomogeneous equation. And the first thing one does is solve homogeneous equation. And that says we put the right side to 0. And one guess the most general form of the W, and most general form of the W is, for example, one might forget that we have this x prime, and then it's just a linear kind of a function which always is 0. But in this case, if we take derivative of some constant which depends on x prime, it is also treated like a constant, because here we take derivative with respect to x instead of x prime. And yep, so we say that we have W in this form. Then we can proceed and apply boundary conditions to find the W. So the boundary conditions, to see how to apply them, appropriate boundary. Yep, we want to find generals of function of W. So we draw the picture. We know that from the text of the problem that we have, the boundary is at x is 0 and the boundary at x is equal to L. And at these particular points, the boundary condition is such that no particle travels. So no particle sits on the end point. So the probability is that particle would go from that point to another point would be 0 at any time. And right, so, and we also know that at some middle we have some singularity the delta function which we skipped from by assuming that W is homogeneous equation. So we treat them separately and we say that there is some singularity x prime and separate the regions x smaller x prime and x larger than x prime. And we write the homogeneous generic form of the homogeneous solution. And also previously wrote it in this way. And it's kind of convenient to not always write the other side in the same fashion, but we subtract the constant. So in a way, this is if L times B2x prime is a form of A, and it's convenient to subtract it in here because if you apply boundary conditions, this part becomes 0 and this also becomes 0 on the left side. So we immediately see what A2 is without actually any without getting into the pitfall of additional step of solving equation. So we know this boundary condition, and the boundary condition, since W is given as an integral, then if we integrate 0 or to infinity, we still get 0. So it follows that not written the Wx smaller than x prime, where x is, let's say, 0 x prime, we still get we have 0 because of this condition. And the same thing for the right side. And when we apply them, we see that these ones are these ones drops out. We only need to find B1 and B2 to find a general solution. So we proceed with we sticking these two solutions together. So I separated them in the half. Now let's stick them together, and two conditions. The first one, that we expect that the solution is going to be continuous. There was not going to be jump. Physical explanation is that so it's continuous there, and we want to join these solutions x over prime and x over x prime. And the second condition is that the second derivative experience a jump. So to draw it more accurately, so we might draw a line. We might need to find a jump in the second derivative. So let's see. I think it's like if you would draw it on one side, we would draw a more parabolic shapes than the other one. Perhaps I would say this would look like a jump in second derivative. And right, we have these two conditions. To apply them, the first one to apply the first one is trivial. The second one can be applied as follows. So we shall integrate this the second equation over over some region, and this region over x would be x prime minus epsilon and x prime plus epsilon, and we have this derivative dwx x prime dx. If you integrate the right side over this interval x prime plus epsilon x prime minus epsilon, you get 1 on the right side. That was the idea. On the left side, we see that we have a derivative, and if we integrate derivative with respect to x, we get rid of the derivative, but we get w x prime plus epsilon x prime minus w x prime minus epsilon x prime is equal to 2 minus 2 over d. So that's, sorry, and this is for derivatives dx. And so this is our second boundary condition which we can apply to find the b. And so when we apply the conditions, so when we plug in these b's in the first one and the second one, the first condition, this one gives us relation that b1 x prime is b2 x prime minus l, and the second one gives us this condition b1 x prime minus b2 x prime is minus t2 over d. And this system we can solve, and when we solve the system, we find w's and obtain the solution. Right, so now we have the solution, and the goal of the exercise was to calculate the correction for, not the correction, yeah, the correction to conductance to the vehicle equalization, and now we just plug in the formula, the solution into the formula. So we plug this inside. So we were given this one, and since we can change the integration, it's from 0 to L wx dx. And since we know this solution, we plug it in and obtain that it's gq over 3. So substantial in low in a low conductance limit. Right, so this is a solution to the first exercise, and let's see if you have any questions. And yeah, ask questions. And cannot find the chat. Okay, I had a question on the chat. For question, how do you derive the boundary condition with the first derivatives? Question 4, how a derivative takes a derivative. The time was 12:05. Okay. All right, so I can repeat this. So we have this condition, and So the next step is to integrate it over x, because we cannot apply the delta function directly, but we can apply the consequence of it. And we take this integral x prime on x prime minus epsilon, so where the delta function is just jumping over. And when we integrate it, as I show it here, we can get this condition here. Right, and x prime plus epsilon and x prime minus epsilon corresponds to wx smaller than x prime and wx larger than x prime. Okay, thank you. Right. Okay, I'm switching to the next exercise. And this one is about resonant qubit manipulation. And so we have been given Hamiltonian for this exercise, and we now want to know how we want to do some transform the equation for rotating wave approximation, but actually not doing the rotating wave approximation. So it's interesting. And then we do some perturbation theory. Okay, so we start with this Hamiltonian where we have a sigma z, meaning so it's just a spin-man half system. It could be an electron in a magnetic field where we have a z component of magnetic field and magnetic field in x direction, which is oscillating. And this one, and this oscillating field is going to give our interaction. And right, so, and we have sigmas as usual. And the first question is to prove explicitly the formula for taking exponential of I, B, Z, sigma Z, T. And yeah, formally, as asked by Taylor expansion, we just use but the definition of exponential. And then when we take the definition of what is exponential, it's actually missing a part, I guess. Sigma Z. I guess it's missing a part, sigma Z n, and sigma Z square is 1, and right, and then one can actually one did this all right, sorry, sigma Z is like this one. And right, we were asked to expand it in cosine and sine. So first we get it in this form, and then we can process each of them separately to get the form in sine and cosine. All right, that is the first task. The second one is more interesting, is to change the variables. So this is the old one. Yeah, the old one and the new one. And by this relation. So for the old one, we know that we have a Schrödinger equation. And the question is, what is equivalent form of what comes out, what equation comes out for phi if you apply the Schrödinger equation? And it's actually an interesting exercise that so to sketch how one does this, one takes so one first write psi of t is exponential minus I b z sigma z t phi of t, and the derivative when one takes which we already, let's put it here. For the left side, it's I h bar, and the derivative is minus I b z sigma z t e minus e b z sigma z t phi of t and plus e b z sigma z t times v dot of t. On the right side, according to the equation we have, is let's see, it's we now put the Hamiltonian. The Hamiltonian was given in the previously, and also with exercise. We put h bar b z sigma z psi, but psi is described as minus b z sigma z t phi of t and plus h bar b x sigma x cosine omega t e I v z sigma z t phi of t. And here comes the revelation that these ones and this one times the coefficient, of course, is equal. So we can drop them out. And now we have this exponential factor, and we have h bar here, and we can write this equation in the form I times phi dot of t is bx cosine omega t and plus ibz sigma z t sigma x e minus e z sigma z t phi of t. And right, so, and it's almost the solution. And the last part is just to process sigma x with sigma z, and they always do it I never do it in often don't do it on paper, but yeah, I always think about the Euler form of this I b z sigma z t, and I also know the formula that sigma z sigma x is minus sigma x, sigma z. So essentially, when one switches the order of them, one gets it with opposite sign, and then applies the sigma x. So it's just some algebraic simplification, and one can get this formula in this form. So that was the second task, and we see the importance of now the interaction becomes much clearer. And let's now see. We are asked what happens in the resonant driving limit, and it is expressed when omega is 2 sigma z to 2bz, and in such case, I have put a cosine omega d in exponential form. So it's there are two possibilities how to proceed. One way is to expand this in cosine and sine and see what happens. But this actually form is much better. We expand cosine omega d in its complex form and multiply the matrix with them and put the stuff together afterward. And we see that we have a constant part and we have some fast oscillating part in the equation. And the idea is that if we would, so what's described after the task 3 is that if we would look on average of psi over t, let's say, and the average is such that the period is such that it's this is larger than the period. The averaging time is larger than the period of this things. Then, essentially, to get such long time average dependence, we could drop these terms out to get this average. We could say it's average over omega. And yeah, and that's would give some result, analytical result describing this qubit behavior. Right, and then we could actually, knowing this solution, one could approximate the fast behavior. But this exercise uses a different method, and the method is a perturbation theory. So we proceed with resonant driving, and we know that we can write the equation in the following form, and we know the initial condition. Initial condition we know for phi of 0, we know from psi of 0, because at this time 0, as remember, the phi was related as exponential I b z sigma z t psi of t, but if time is 0, we just say that at 0 phi 0 is equal to psi 0, and as exercise says, it's the spin is just down there. And the next step is to use the perturbation theory, and the perturbation theory is such that we expand in bx, and bx is actually this. We expand in terms of the sometimes in the right side. It could be possibly done if bx is small. So we know the usual expansion, how one does, and the plus bx cube. And right, and substitute it in. Let's see if I have written it. Yeah, I have written it down. And now one recognizes a fact that, interesting fact indeed, that we need to apply boundary conditions. So we now psi 0 and for phi 0, and phi 0 is 0, 1, and here we have multiple terms. The idea is that when we apply the boundary condition, we say we get it that phi 0 is equal to 0 order phi 0 at 0. And the idea behind is that our initial condition would be the same for different bx. And since it is so, so it's constant in bx. And the constant in bx we apply to the first term. Right, that's how we get a boundary condition for 0 and phi n of 0, 0 are 0 because, yeah, because of our initial condition. Right, so next step, we first write the equation in the cup in usual form, and we substitute the expansion, this one, in it. And we substitute it to the first order. And what we get is that phi down first order term of t is 0, and phi up of first order term in time is as follows. And it's interesting, well, what happens often when we drive an oscillator in a resonant frequency without friction, the amplitude of oscillations grows linearly, and that's it actually we see here. And right, and so to conclude, the result holds only when bxt is much smaller than 1. Otherwise, but what follows since the correction to the first order first time is 0, then and we get the corrections to the first term, then the probability wouldn't be unity would not be conserved. So this is the condition, so that electron, the number of electrons, so the probability of the both states would be 1. Right, so that was the last question of this exercise. Let's see if you have any questions. Can you explain how you do it? Equation on the bottom of the slide of question 4. This one. Okay. Right. Yes. So this bottom part is coming from here, And now we can substitute our perturbative expansion. It's phi up 0, 0 plus bx phi up 1 at 0 dot, and on the right it is bx over 2 1 plus e to 4i bzt, and phi down, what we know about phi down is, okay, we shall substitute actually. It's phi down 0 plus bx phi down 1. And the point of the perturbation theory is that we are looking at the same orders. So bx times bx would be big X squared. So we can drop that term. And phi up down, we actually don't, we know that it's 0, so not much to consider. And right, and this gives us a correction correction to bx to phi 1 phi up. Right, so and right, we know that this is equal to 1. And perhaps the difference between what I have written. Oh, okay. It just finishes. The difference between what I have written here to get the result here is that there is no bx, but the bx is easily restored. Just it's often the case when sometimes one writes bx and one sometimes forgets to write this bx square. And there, yeah, but both kind of results are fine. But in this case, which one would be accurate for the things we have written here would be writing it down here, but the condition would remain. Can you explain how you got the initial condition? I missed that initial condition. So we know this initial condition, and right. So, and we know that initial condition does not depend on bx, and we know we expand the pi of t in terms of bx. So the condition, initial condition, only applies here. Does it answer the question, or there's something else? Why we start in 0, 1 out transpose? So that's actually, you look on the conditions of the exercise, and we describe, we look on the not conditions, but the statements made in exercises. We describe a qubit by the two component wave function, psi of t, psi up and psi down, and psi L0 is spin down state, which we represent. Okay. yeah, sometimes it's given in the beginning, but you kind of don't use it by the last part of the exercise, so it's confusing, but yeah, it's a way. All right. So I think we already made 45 minutes. Let's move in the last exercise. All right, the last exercise is about describing a 2-qubit system. And it's interesting that, so not interesting, but the system is that we have 2 independent qubits, which are described by like qubits being independent in some magnetic field, and this magnetic field is assumed to be equal. And there is a coupling between the 2 qubits, which we can tune at our wish at any given time. And what we want to get from the system is C0 gate. So the gate is just a unitary operator. Is some unitary operator which we get executing some protocol in terms of magnetic field, which we apply in given time, or coupling at given time. So let's start with task 1. It asks for G int 2-qubit gate. We have been given a interaction time. Tau is pi over 4h/g, and right, we want to know the unitary operator of that. So we know that unitary operator is given as exponential. So since Hamiltonian is at the time independent in time, so we can get unitary operator in this way. And we know that h int is expressed as follows. So this is a 2-qubit gate, and when we put this sigma set together, there is a tensor product in between. We get the following operator. And to understand this operator, we just have to put the labels just down, up, down, down, and up, up, and the same for the right one. Down, down,
down, up, up, down, down, down. And if we look on this one, for example, we know that sigma z is 1. So sigma z is 1 minus 1. So 1 comes from the left, the first part of the qubit, and another one comes from the second part of the qubit. So we get it 1. And the same is true for this up state. So we get from one qubit minus 1, and the other qubit another minus 1, and in the end we get 1. And the opposite signs we get when we have states with opposite spins. So we were asked to apply this h int to our time as given, and when we apply it, we get that. So we put this h int in time here, and assuming, I guess, that the magnetic field is 0, and we get it in following form. And to get it in the form we want is we set out the e over pi over 4. So we have something which looks like a gate 1 minus I 1. Okay, so that's task 1. The second task is about rotating the qubits separately. So a rotation operator on any qubit can be given as follows, that we have this usually is a magnetic field times sigma, usually some time, but there is some sigma, there is some rotation over theta over 2, and theta over 2 is there because qubits, we can rotate qubits over angle of 4 pi, and as you can see, going to see, it's interesting that we can also rotate 2-qubit systems. We need more 2-qubit system, we need more angle. There is more space to rotate. And right, so we have been given a suggestion, I guess, in the space of qubit. Right, there is no rotation suggestion, I guess, for this. Yep, we need a rotation. Okay, we need a rotation RZ, which is minus I and I. And it turns out that that we can get if we rotate a single qubit by angle of pi over 2. We rotate it pi over 2, and if we divide by 2, we get it over pi over 4. And that is our rotation we get for a single qubit. Now we want to, not the rotation we give, but that explains what is this minus I. And now we want to apply this operator on qubit 1, and we want to apply it on one qubit only, and then on the other qubit only on one, and only on the second one. So, so this is 1 qubit operator. The next step is to get a 2 qubit operator. So how we do is Right, so we remember that we have a state. The ordering of these states were down, 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 up, up, down, and up, up. On the right, we have down, 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 up, down, and up, up. And we know that the operator applies only on a single qubit. So what we actually have is we want R, so example R set 1. What it actually contains is RZ tensor product with identity. So it doesn't do anything on the second state. And ours it applies on the first state. We look on the spin of it. The first spin is down, so we put a minus sign in here. Here we see also the spin is down. We are going to put this element there, and the spin is up in the first one, and we put up and up there. And the second one, error set 2, it is similar that we have identity, and we only look on the second. The element of the second spin, and that describes how we get this matrix. And for convenience, or visit task, we take out say e to I p over 4, and we get something which looks like a gate here. Okay, so the next question is to use these all three operators, G int, RZ1, RZ2, to control the controlled Z gate. And it turns out if we multiply them all together, so you know the form, how you know how to multiply matrices, we can get it in this form. And it looks like this is, and we see that this is a CZ gate, and there is some constant prefactor. Often one just drops these constant prefactors on the basis that if you consider the full system, then you don't measure them. And so this one actually can be dropped, but we just keep it to see the final result, how it looks. Because it's kind of relevant if we have 2-qubit system in a subsystem of multiple qubits for example, in quantum computer. So then it's relevant that what we have there. And the last question is to use a Hadamard gate to get the Hadamard gate for qubit 2 and no action on qubit 1. So Hadamard gate, and right, Hadamard gate on the qubit 2. So QH2 is identity, a tensor product with H. And as it turns out, so the states is up, down, up, down, up. It's kind of a funny ordering. Down, up, and down, up. I think I have made small mistake here. But we would have, so the ordering, which is unfortunate, is not equal to this one. If we would do it in this ordering, we would need to switch orders of this one with this one. So it would turn out that it's 1 and -1 here and +1 and -1 here. But yeah, that's just a minor detail. And in the end, we have this Hadamard gate for the second qubit, and now it's time to apply to our CZ gate. And CZ gate we can represent as I sigma Z and if we would have fixed the ordering, oh, it's frozen. No, I think I froze it. Unfortunate. But yeah, the screen is on, and this is the last slide. So we have this CZ, and oh, we don't have slide at all.
No device emulators found.
yeah, I see. It's unfortunate that oh, my table restarted. Yeah, it was the last slide. It's so unfortunate.
That things happens.
Right. Let's rotate it. Let's see if we can get it back. Yes, we got it back. So yeah, so the last slide we have obtained the CZ gate, but if we actually would do sign by sign, the ordering was a bit unfortunate. The ordering was unfortunate, and we would get a minus here. Can I write it? Yeah, we get a minus here. Instead, if we would get, if we would change the ordering of the states, and right. No, how we can represent this state? Well, maybe we could just represent this one with tilde to have the ordering we have chosen. And right, when we would apply this Hadamard gate of second qubit to our CZ gate we had obtained previously, which had some global phase factor, but we in this currently not interested in. From both sides, we would get a C0 gate. And right, so we can, in the end, we can write our final C0 gate as a combination of 1, 2, 3, 4, 5 qubit gates. So it will be a little bit noisy, depending of course of the system. And right, and that is a way how one obtains, how one thinks about different gates for how to implement different gates. For example, on quantum computer, it's just matrix multiplication. And we saw that if we have 2 qubits, we have 4 states, but if we would have 3 qubits, we would have 8 states, and it would grow exponentially. So these matrices gets increasingly large. So that's the advantage of quantum computer. Right, so this is last question to this exercise, and I don't see any questions you asked now, but let's see. Right, so I guess I don't see any questions here, so thank you for listening to my presentation, and yes, have a good luck on exam.
All right, that was the last regular session for you. We kind of end our course. If there are any questions, please contact me and Yanis. Otherwise, we will see each other at exam. I reckon you understand how exam will happen. We have had a preliminary exam. Everything should be clear. But in case of any questions, please don't hesitate to contact me or Yanis. So with this, I shall thank you for your participation. The course is over. Bye.